Another gentle reminder as we start with the online coding session. Do use our Slack channel for any questions and keep the discussion going. Use our channel #build DS project. And for any questions and queries, do put it in chat. So I'm excited to introduce our speaker for today. We have Siddhi Purohit. She is a B.Tech student and is set to become a software engineer at JP Morgan and Chase. With a strong IT foundation and a keen interest in machine learning, she has worked on various projects, including image generation, predictive analysis, and activity detection. Siddhi has gained hands-on experience applying ML techniques to real-world problems. She has actively participated in hackathons, showcasing her competitive spirit and determination. She is committed to empowering women in technology and serves as an evangelist at the Women Who Code Data Science track. She also enjoys music and cultural exploration, listening to classical pop songs and exploring different cultures. Siddhi, we are very pleased to have you here today. And I'll stop my screen share and hand it over to you.
Thank you so much, Mrudula, for that warm introduction. I'm so happy to be here. Just give me a second, I'll share my screen. Mrudula, can you let me know if it's visible to you?
Yes, it's visible.
Is it still visible? So can we start then? All right, perfect.
Yeah, sure.
Okay, so thank you so much to everyone who has joined in for this session. I know that for a lot of you, you must be joining either late at night or early in the morning. So I really appreciate you all taking out time for this session. All right. So before we begin with the session, I would just like to lay down the agenda for today's session. We will talk about the importance of model selection and process today. What is the importance of underlying statistics of how those algorithms will work. We will also talk about some common advanced models, the complexity of models, how we can tune and optimize our models, and finally, how we select our models. And at the end, we'll see our use case using on our collab work. All right, so what is the significance of a model selection? And also, I would just like to tell everyone that this will be a little dense session, and I'll try to cover as much topics as possible and in as much depth as I can. But definitely feel free to put in your queries in the Q&A, and I'll try to take up them as much as possible. All right, so what is the significance of model selection, right? See, model selection is a very important role in the success of a project, because when we are using well-suited models, they will impact the performance and accuracy of our predictions. To ensure that the model's assumptions align with the characteristics of the data, the solution and the use case, there are certain points that we have to keep in mind, right? First is that what is the real world consequence of our results, right? So whatever the results that we're getting from a model results and the deductions that we're getting from those results, are they aligning with what we wanted to achieve out of our model? And the second is that if we are not using proper models, then they may underfit or overfit the data. So underfitting and overfitting is a very common term that you'll find often in your projects. So overfitting is the concept wherein your model will perform really well on training data, but it won't perform well on your unseen or test data. Whereas underfitting is the concept wherein your model performs poorly on both your training data and test data, which essentially means that it is unable to capture any underlying patterns in the training data. So now that we know the significance of model selection, we will now see what is the process for model selection, right? So the first step in selecting our model is to understand what is the problem definition and data understanding. So as we saw in the previous sessions, for our particular use case, our problem definition is to find out whether a song will be live or not live. And For the data understanding, we have seen in the previous sessions that we are using a Kaggle data set, and we have seen the different features that our data set has, right? Like, for example, we have different features like acousticness, danceability, which tells us which all are features, and we're trying to find out from these features and trying to find certain underlying patterns, right? And to see from these features, are we able to tell whether a particular song will be liked or not? So once we have an understanding of problem definition and data understanding, we move on to feature selection and data preprocessing. So just a brief overview, feature selection is nothing but the process where we select important features, and data preprocessing is the task where we clean our data. For example, we will change our categorical data into numbers, right? Because at the end of the day, our machine learning model is nothing but maths. So it doesn't understand text. So you need to convert all your textual or categorical data into numbers, and then you have to standardize your data. So all of these steps you have to take, all these come under data preprocessing. Before I move on to the next step, I did want to just have a quick chat, with you. You guys can reply in the chat. So for feature selection, let's take an example of a data set. And this data set has the order history of one particular Amazon user. So we could have different features, right? We could have different features like, say we have this one column of feature in your data set, which tells the unique, which is a unique identifier for each order, right? Second feature we could have is probably the price of your order. Third feature could be the category. So as you often see on Amazon, that your items are often categorized into different categories. So you could have a column specifying which category it belongs to. And then you could have maybe fourth category as the name of the item. So can you guys quickly tell me in the chat, out of say the four columns or the features I tell you, which column would be the most irrelevant for us? Feel free to use the chat to drop your answers. Yeah, exactly. Thanks, Nasreen, Vati, and Tejaswini for replying. Exactly. So as we see that order ID, or that column which give you the particular identifier for each order, would be the most irrelevant feature to us, right? Because it's not giving us any extra information. Therefore, it becomes a redundant data set. So in feature selection, our task is to drop or remove these redundant data sets, which won't give us any new information. So after second step, we move on to algorithm selection, which is based on different problem characteristics. So in our particular use case, we are trying to do binary classification. Why? Because we have to identify whether a song will be liked or not liked. So we are classifying it into 0 or 1, wherein 0 signifies a song is not liked and 1 signifies a song is liked. So our problem statement or problem characteristic here is binary classification. So our concept here is to find machine learning algorithms which will help us in the binary classification. So those are the ML models that we'll focus on. Once we have those, once we select those appropriate algorithms, we then do hyperparameter tuning and model training. Brief overview of hyperparameter tuning that we discussed in the previous sessions as well. Hyperparameters are nothing but knobs that you can tweak, right? So that you can increase your model performance. And finally, we evaluate and compare our models to find out which model with which set of hyperparameters will give us the best performance. Now we need to understand why studying statistics and algorithms matter. When we're studying machine learning and algorithms or models, as I said, they are maths. So we need to understand what is their underlying statistics, because each machine learning model has its own assumptions and limitations. So we need to understand what those limitations and assumptions are, so that along with the characteristics of a problem statement, what kind of data we are choosing, so that we can choose the most appropriate machine learning model for our problem statement. For instance, linear regression is used for regression problems. I cannot use linear regression for a classification problem, but I can definitely use logistic regression, which can be used for classification problems. So if I'm not aware of the underlying statistics of the linear regression, and if I use linear regression on our particular use case, which is a binary classification problem, then I won't get my suitable results. So that's what we have also written on the slide, that it gives you an enhanced ability to choose appropriate evaluation metrics. It increases your skill in selecting right algorithm and hence fine-tuning the hyperparameters. It gives you increased interpretability and trust in your model results. And of course, it gives you better, it makes you a better decision maker and avoiding any common pitfalls. We'll quickly just discuss a few common and popular advanced ML models. We have SVM, which are support vector machines, random forest, as you can see on your screen. These are all supervised learning models. Again, just a quick refresher. Can anybody in the chat quickly tell me what is supervised learning? And it's all right. We are learning here, so you can, I mean, I would encourage you all to put your thoughts in the chat box. Perfect. Yes. Yes. So you all are right. Supervised models are where the labels are known to you, right? So you have a ground truth available in the data set and your model learns from it. Whereas unsupervised is you don't have ground truth available to you, and the model has to find underlying patterns. And with those underlying patterns, it tries to, whatever, it could either classify or do a regression problem. All right, and on the next screen, you can see, again, linear regression, decision trees, neural networks, very popular machine learning models that you will come across in your daily life. Then we have collaborative filtering. These are a little more complex models, which are often used for recommender systems. So you must have seen when you use Netflix or Spotify, you often get recommended, you often get personalized recommendations, right? So how are those happening? So you can use these collaborative filtering and matrix factorization models for recommender systems. Similarly, we have k-means, hierarchical clustering, which are used for the purposes of clustering. And we also have the, and then there are also large language models like BERT, GPT, even ChatGPT that's very popular right now is a large language model. And these models are essentially used for language understanding or language generation, language translation. They are related to language and text. So moving on, we'll understand the complexity of a model. How complex should our machine learning models be? It's a very important question because ideally, we would want our machine learning model to go as complex as possible, right? Because we want our machine learning to learn as much parameters, as much data from your data set and the feature set, right? But the problem is that as your machine learning model becomes more complex, it will definitely perform really better on training data because it has much more parameters to adjust and gain a better fit from the training data, but it will end up overfitting. And as we discussed before, okay, before I tell the answer, why don't you all tell me in the chat what was overfitting? You can put it in the chat what you believe is overfitting, and then we can move on. And it's fine if you don't remember, I can tell it to you. Okay, I didn't see those texts. Train is performing well on training set, but poor on test set. Exactly. Thanks, Nasreen and Tejaswini. That's exactly right. Overfitting is the model will perform really well on training set, but won't perform well on test set. Now, moving on, we'll discuss what are the ways to tune your model. So the first option is using hyperparameters. Let me quickly go to the documentation here. This is the documentation of logistic regression. I hope you guys are able to see the screen. If not, just put it in the chat. Okay, I'm assuming that the screen is still visible. So as you can see, this is the documentation of logistic regression. And I would, on a side note, I would encourage you all to refer to the documentation of machine learning models. sklearn is a great library. They have great documentation, and often most of your doubts will be cleared by referring to the documentation. So as you can see in the documentation here, there are different parameters here: penalty, dual, C, fit intercept. Um, all these parameters are basically all the arguments that you give in the function of this machine learning model, right? And these are nothing but your hyperparameters. So coming back to the slide, when we say we have to model tune, as I said, we are doing hyperparameter tuning, which is we are tweaking the knobs so that our performance of a model increases. How we can do that? There are three ways of doing that. First one is grid search. So grid search is wherein you will exhaustively search a predefined hyperparameter grid so that you get the best combination. Random search is, instead of exhaustively searching all the hyperparameter grid, you will randomly sample from the hyperparameter space. And in Bayesian optimization, you use probabilistic models to find promising hyperparameters efficiently, which essentially means that you're taking into account how the previous combination of hyperparameters work. I will go into detail about this later in the session, because we also have our session notebook wherein I'll be able to explain it in much deeper context to you guys. Following that, another way to tune your model is using cross-validation. Now, cross-validation is a very popular method to tune your model. So cross-validation is a way that you can assess your performance and generalization ability by evaluating it on multiple subsets of the data. So essentially, you divide your original data set into multiple subsets, also known as folds. And with each subset, you're training your data on each subset. And this is a great method because it increases the reliability of how well your model will perform on unseen data compared to a single trained test plate. Again, with cross-validation, there are different ways you could do it. There's k-fold cross-validation, wherein you divide your data into k equally sized subsets or folds, and your model is trained that many times, which will be k times. So your each fold will serve as test data once, and the remaining will, all the remaining folds will be considered as training set. Then we also have leave one out cross-validation. This is a more rigorous form of k-fold cross-validation, you could say. Why? Because here, instead of dividing our data into subgroups, we are considering each observation or each row as a separate fold. And we will leave out one observation each time. So if there are n rows, then your there will be n iterations of your data set. And then finally, we have stratified cross-validation. So stratified cross-validation is used when you have imbalanced data sets, and it ensures that the class distribution is preserved in each fold because it reduces bias in the evaluation. So stratified cross-validation involves stratified sampling. Stratified sampling means that, for instance, you have your original data set with two classes, male and female, with the male percentage being 46% and the female percentage being 54%. I hope these numbers are right. And they're adding up to 100. But anyways, so if this is the ratio in the original data set, stratified sampling means that we are creating such subsets such that the ratio between those two classes remain the same in each of those subsets. I'll quickly go through the chat to see if there are any questions. All right, I do see one question, but I can take it up at the end. All right, so moving on, what are the advantages of cross-validation? As we can see, it will give us better performance instead of a single train test plate because we're reducing the randomness, and it is making it much more reliable because we're training it on different subsets. Secondly, it is used for model selection. So cross-validation can be used to compare and select the best model among different algorithms or hyperparameter. And it also gives a robustness check, as it helps us to assess the stability and consistency of the model by evaluating it on different subsets of the data. There are definitely some disadvantages. It is computationally intensive because you're training your data much more time, much like multiple times, which is definitely time consuming, especially for large data sets. And then there's another concept called information leakage. So information leakage from the test set into the training set can lead to overly optimistic performance estimates or thinking that a model is better than it actually is, right? And it might perform well on the test data, but it may not perform as well on any new or unseen data. And this can happen if we perform feature selection or pre-processing steps on the entire data set before splitting it into training or test sets. Following, we will see how we can optimize our model. So to optimize our model, the first step is to have a good model selection. So again, for a good model selection, we need to compare different models with different algorithms, and we identify which one is performing the best. We also consider factors such as what is the complexity, what is the computational requirements, and the suitability for our problem. Followed by that, we do feature selection and engineering. As we had discussed before, feature selection is identifying relevant features and removing irrelevant one. And sometimes we can also create new features that can capture important patterns or interactions in the data. Another method of optimizing your model is known as ensemble methods. So ensemble method is the concept where you use multiple models to create a stronger and more robust ensemble model. The goal here is to improve your prediction accuracy, handle complex relationships, reduce overfitting, and enhance generalization. There are several techniques such as bagging, boosting, and stacking, which we'll discuss in detail in the next slide. So there are three popular techniques of or ways of doing ensemble methods. The first one is bagging. So bagging is also known as bootstrap aggregating. In this method, we are combining different models which are trained on different subsets of the data obtained through bootstrapping. So bootstrapping means resampling with replacement. So for instance, if you have a very simple data sample of say 100 points, right? And from those 100 data points, you have to create subsets. So when you're creating those subsets, you're taking each data point as an individual data point. So okay, let's understand it like this. You have a sample data with 100 data points, and I've created 3 subsets. And in all of those 3 subsets, I can have multiple instances of the same data set. Why? Because when I'm resampling it with replacement. And this concept is known as bootstrapping. So when each base model is trained independently, the final prediction is determined through aggregation, such as majority voting for classification or averaging for regression. Random forest is a popular bagging ensemble, which combines multiple decision tree. So to understand this better, random forest is an ensemble of decision tree. So you can understand that you have this original, you have your original data set, and you create subsets on your original data set. So for example, we have created 3 subsets, A, B, and C. And on each subset A, B, and C, we will apply a decision tree model. And for our problem statement, say we are doing classification, right? So from each subset, and from so what I'm saying is that from on each subset, when we apply the decision tree, we will get a certain value that could be either 0 or 1. And so say from those 3 subsets, we get 0, 1, 1. And so the majority voting says that 1 is what you should classify it. So that's what I said in the second point, that the final prediction is determined through aggregation, such as majority voting for classification or averaging for regression. And random forest can be used for both classification and regression problems. So I hope you understood how random forest is an ensemble method. If not, when we'll see the collab book, I think you'll understand it better. Now we see what is boosting. So boosting builds an ensemble by sequentially training multiple weak models, wherein each subsequent model will focus on the sample that the previous model struggled to predict correctly. So it essentially assigns weights to observation, wherein the emphasis is more on the data points which are harder to predict. An example of boosting is gradient boosting algorithms like XGBoost. The last method is stacking. So stacking basically combines your predictions from multiple base models by training one meta model. And the meta model then learns to make predictions on the outputs of these base models. And it essentially allows for the exploitation of different model behaviors and can lead to improved performance. The advantages of ensemble method is it will give you improved accuracy because you're leveraging the knowledge of multiple models and you're reducing bias and improving the prediction accuracy. Second is it can handle complexity. Our problem with single complex model was of overfitting. With ensemble, we can still have a complex model, but it can reduce overfitting because it will be because it can capture much more nonlinear patterns. And again, reducing overfitting we have discussed right now. And last is feature importance. So ensemble methods provide insights into feature importance by aggregating information from multiple models. There are certain considerations that we have to check during while you're doing ensemble techniques. First is model diversity. So ensemble methods benefit from diverse base models when they are able to capture different aspects of the data and they're able to reduce errors which are caused by individual models' weaknesses. There's computational complexity. So ensemble methods are generally much more computationally expensive and they definitely require much more resources than any individual model. And for hyperparameter tuning, ensemble methods have their own additional hyperparameters that can be optimized for a better performance. Another method of optimizing your model is known as regularization. So regularization is a concept which is used for preventing overfitting. As we said that overfitting is a very common problem we face as our model becomes more and more complex. So to avoid overfitting, we employ regularization, which is nothing but adding a penalty to the loss function, which discourages the model from learning overly complex patterns in the training data. Your regularization can be of two types. You can have L1 regularization, wherein the penalty is equal to the absolute value of the magnitude of the coefficients, and L2 regularization is where your penalty is equal to the square of the magnitude of the coefficients. And regularization helps you to control model complexity and penalize large coefficient values. So once we've optimized the model, the next step in model selection is evaluation and validation. We will use appropriate evaluation metric based on whatever the problem type we have. So in our particular case, our problem type is a classification problem. And once we have selected our evaluation metric, we validate our model on independent test set to ensure the generalization. Another important point is retraining. So it is important that you're constantly retraining your data and your model because of various reasons. There could be a change in business scope. Often you will have new data being added to your data set, or they could be for model maintenance, for performance monitoring. So it is always a good practice to retrain your model. Now we'll move on to our collab file, wherein we have discussed the following models. We have discussed logistic regression, decision trees, random forest, and XGBoost. Before I move on, all right, I don't see anything in the chat for now. And for Q&A, we can have it later. All right. I hope the screen is visible. So, all right, so we'll start looking at our code now, because it's always great to refer to any code to understand, to get a better understanding of all the concepts. So first and foremost, you need to import all your important libraries and packages. In the first code cell, you can see we are installing XGBoost, which will be later used for the XGBoost machine learning model, followed by the different libraries, for example, pandas, sklearn, matplotlib. Now, the first thing is you have to obviously load your data. So we will use our clean data. In session 3, when we had done pre-processing and visualization of the data, you can refer to the session 3 on our GitHub, and you can get the clean data from that particular repo. So once we have uploaded or hosted our clean data, we then move on to pre-processing. So in the pre-processing step, our first step is to scale the data. So for scaling the data, we are using a function called standard scaler. So standard scaler is a great choice because of three reasons. First, it is great at outlier handling. So outlier handling is important because when you have outliers, it can tend to squish your data into a much narrower range because of the outliers. But standard scaler, on the other hand, it does not have a fixed range. Therefore, it's not affected by outliers. Another reason is algorithm requirements. So there are certain algorithms which assume your data is normally distributed or symmetrically distributed around the mean. So standard scaler makes the mean of each feature 0 and the variance of each feature as 1. So it is distributing your data normally. Therefore, it could be a great reprocessing step if your algorithm makes this assumption. The last point is interpretability, because in standard scaler, you are making the mean 0 and the variance as 1 for each feature, right? So essentially now what it is telling you is that it is telling the standard deviation from the mean. Therefore, it becomes easier for you to interpret the results than maybe using a min-max scaler. So in our data set, you can see that in our Spotify song attributes data set, we have various attributes like acousticness, danceability, energy, and all these features have different scales and can also contain outliers. Therefore, we use standard scaler. Just a side note, although scaling is not necessary for tree-based models because they're not sensitive to scale, it is still beneficial that you use standard scaler, because when you will be comparing your tree-based models with non-tree-based models, it's always best to have uniformity, and therefore it's better to use standard scaler. Moving on, we will prepare and split the data into train and test sets. Before we do that, it is always a good standard practice to check the class imbalance. So what I've done in this particular cell is that I've taken the target variable and found the value counts of each category. So as we can see on the screen, the counts of each category. In the next cell, I've just taken it out in, I've found the percentage of each category in the target column. This wasn't a necessary step here, but it's always a good practice to find out the percentage of your categories instead of noting them down in absolute values. So as we can see that the imbalance there's almost negligible imbalance. It's 50 to 49%. Therefore, the class imbalance is negligible, and we can simply move forward and standardize the data. So before we do that, we are simply separating the target variable from the data set, and then we are checking the data type of each column. Again, a standard practice, you should check the data types of each column in your data frame. Why we do that is you'll understand in the next step. So in the next step, you will see that we are selecting all the numeric columns from our data set. Why? Because only the numeric columns will get standardized. Therefore, it is a good practice to know how to, it is a good practice to select all your numeric columns in a list. So that's why I said that it is a standard practice to check what are the data types of your data set. So once we select the numeric columns from our data set, I've created a function here that will standardize all the numeric columns. I think you will better understand it from this cell. So the standardization is the function that I've created. What it is doing is that it is taking X, which is your data set, as your first argument, and it is taking numeric column, which is the list of all the numeric columns. Fortunately, in our data set currently, all of the columns are numeric in nature. So in what is happening inside this function is that it is iterating over the data set, and as it is finding a column which is also present in the numeric column list, it standardized that particular column. But as I said, that since all the columns in our data set are numeric in nature, it essentially standardizes all the columns of our data set. And you would be able to see the difference in the columns here because now they've been standardized. Now we move on to model evaluation. we have discussed three methods. The first method is model evaluation without using a validation set. So we will import the libraries, we will divide our data set into train and test sets. The first method that we'll apply is a logistic regression. And we will evaluate it on accuracy. Why? Because the classes are relatively balanced, as we saw before. Just a refresher, accuracy is nothing but the proportion of predictions that the model got right. Now, I won't be able to go into details of all the machine learning models, but I definitely want to just give a brief overview of how logistic regression works. So I'm going to jump up to my Jamboard. All right, where's the pen? All right. So to understand logistic regression, we first need to know what is linear regression. Okay. So linear regression is a model wherein your model tries to make or predict the best fit line that will best fit all the parameters. I think this felt a little bit like jargon. I'll try to explain it with this. So consider you're making all right, so consider this is your graph. Okay, so say this is your X, Y, and Z. And X, Y, and Z represent the different feature set of your data set. So in our data set, again, I'll just go back here so that you have a better idea. So for instance, if we only take acousticness and danceability here, okay. So I can represent danceability with X, and Y I can represent with acoustability, and Z will be my target variable. And target variable is wherein we want to classify our data into 0 or 1. So what linear regression does is that it will try to find the best fit line in this 3D space, because currently we have taken 3 parameters. It will find the best fit line such that it best fits these data points across it in this 3D space. So it will try to find that particular line which will be closest to almost all the data points. But this is what linear regression does. How will logistic regression work? As I said, that linear regression is only used for regression purposes. It cannot be used for classification problems, because it gives us a continuous value instead of discrete values. So to convert this into discrete value, what we do is that we use logistic regression, wherein we with whatever line we got. So we know that the what is the formula for a line? It is y is equals to mx plus c, right? So what we'll do is that we will apply a sigmoid function on this line that we get, which is the best fit line, and we apply a sigmoid function on this line, which converts this straight line into something called as S-line function. Okay, and when we get a S-line function, when we get this S-line function, what we do is that we create with this S-line function, we can divide our S-line function into 2 parts. So that, and we say that one will be, we can say that any value which is above the midpoint of this S-line function will be classified as 1, and anything that is below will be classified as 0. This is, again, I've just tried my best to give a good overview of how logistic regression works, but I encourage you all to look at the documentation and study on your own after this session to really grasp the concepts really well. So I'll move back to our notebook. So the first model that we'll apply is logistic regression. Why? As I said, that logistic regression is a great base model to do binary classification. And logistic regression is, again, a supervised learning algorithm, and it is very easy to implement and easy to interpret as well. So we have applied logistic regression on our data set, and we have found almost 66% as the accuracy. Similarly, we have applied different algorithms like decision tree and random forest. And as we can see that our accuracy is increasing, with random forest giving us the best accuracy. Another method, which is a good standard practice, is to fit your models using k-fold cross-validation. So as we had discussed before, k-fold cross-validation is nothing but you divide your original data set into different subsets, and then you train your data on each subset. So as you can see here, again, just imported the important library, then we've applied logistic regression using the cross-val score function, which is used for cross-validation. We have taken k is equals to 10, that is, we're dividing our data set into 10 folds here. And that is why I've specified CV as 10 here. And as you will observe, what we get is that cross-val score will return an array with accuracy scores of each split. So as you can see that because we had 10 splits, it will give you an array of 10 values. And these values correspond to the accuracy of each, accuracy corresponding to each fold. So we see that the best accuracy that we get here is 71%. And another thing to note is that cross-val score function uses stratified k-fold for splitting. Refresher, stratified k-fold means that you will be maintaining the same ratio of classes as it was in the original data set. So we have done the same thing on decision trees and random forest. And again, you will see that random forest performs the best with 85% almost as your accuracy. Now we will see hyperparameter tuning. Hyperparameter tuning on random forest, I think, is one of the best way to really see the impact of hyperparameter tuning. So I think I do have, yes, I have the documentation of random forest here. So we have taken n estimator as the hyperparameter on which I am doing the tuning. So n estimator is nothing but the parameter which decides the number of trees in the forest. So going back here, I have increased the number of trees from 5 till 100. As you can see that as I'm tuning this hyperparameter, my accuracy is increasing. So this gives me a good idea that with the greater increase in the number of trees, I can expect a good increase in my accuracy. There are different, you can also tune your different hyperparameters. So in random forest, as I said, you can tune it on criteria, max depth, different parameters, you can do that. Our third method is using XGBoost with validation set. Now this is a much more advanced model optimization. So XGBoost is short for extreme gradient boosting. And we did learn about, we discussed it briefly in the slides before. I will quickly go through it because I see we don't have much time left for the session, but essentially it has several steps involved. So first is initialization, where you will predict a constant value for all the instances in the data set. Then it will do sequential learning, wherein it will enter a loop and it will repeatedly build new decision trees. And each tree will be trained to correct the mistakes from the previous, all the previous trees. Then we do gradient boosting. So gradient boosting comes from the fact that each new tree is specifically designed to reduce the gradient of the loss. Followed by regularization, it will try to, as we know that regularization is used to reduce overfitting, and followed by tree pruning. So tree pruning is a technique which is used in XGBoost, wherein the trees are allowed to grow to their maximum depth during training, and then any unnecessary branches are then pruned off or removed. And finally, we do the prediction. So once all the trees are built, we make a prediction involving, wherein we add up all the predictions of all the individual trees. So essentially, XGBoost has the predictive power of hundreds of thousands of individual decision trees that are involved in it. Therefore, it is a complex machine learning model. So here what we're doing is that we have we are dividing our data set into train, test, and validation. Again, a good practice to use validation test, validation set while you're performing your model evaluation. If not, if you can use this method. If not, you can always use cross validation. Really depends on how you want to start off. Then we have just created a XGBoost classifier object here, and then we train this object. So by training, we mean that we fit the object on our data set, and then we evaluate our model. So as we can see, we get a validation accuracy of 72%. And then we are doing hyperparameter tuning on XGBoost, right? So we have taken these 4 knobs or hyperparameters to be tuned, which is n estimator, max depth, learning rate, min child weight, and also booster and base score. So we have taken 6. And we have applied grid search CV. So as we discussed before, grid search CV will allow you to define a grid of possible values for these hyperparameters, and then it will automatically perform cross-validation for each combination of these parameters. So as you can see here, we have taken a hyperparameter grid, n estimators, max depth. So we have taken all of these 6 hyperparameters, and we have defined the particular values of these hyperparameters on which we want to test. So so grid search CV will do an exhaustive search. That is, it will search for each combination. So it will do 50 to 0.051, 0.05, then it will change 50 to 0.051, then taking 0.5 base score. So it will do an exhaustive search. So as you can, I think you'll be able to identify that it will be a very exhaustive and computationally expensive process, because on top of that, we are also applying cross-validation. So we have like fit our model, and here and in the next column, we have basically found out which the validation accuracy. And as you will see that with grid search CV, it will ultimately return you an array of hyperparameter scores, or the combination of those hyperparameter scores which yielded the best accuracy. So in our case, the array is this. So with base score as 0.75, booster as GB3, learning rate as 0.1, etc. With this combination of hyperparameters, we are getting the highest accuracy of almost 74%. And another method is using randomized search, because as I mentioned that with grid search CV, it's an exhaustive grid space. So you can expect it to be extremely computationally expensive. So to save yourself time and your computational power, you can also use randomized search, wherein it will randomly pick. And there's definitely maths underlying it, that it's not exactly random. It essentially, it is trying to mimic the not mimic, but it's trying to understand what were the patterns before, with which the accuracy is improving. But I'm not going to too much into detail and depth of it, but you can always read up on your own, and it's quite interesting, the maths behind it. So in random search CV, as you can see, yes, so here we have actually printed the best hyperparameters found. We fitted the model, and as you can see that we are actually getting a better accuracy with less computational power. So sometimes random search CV performs better than your grid search CV. All right. So now we have in the next cell, we have predicted the labels, and we have computed the test accuracy. So we see that we are getting a test accuracy of almost 75%, which is a pretty decent score. And to visualize the results, we have also created a confusion matrix. Now it's the important part, which is to understand the observations of our model comparisons. So I'll quickly show you. From all the 3 methods, we saw that random forest with cross-validation yielded us the best results, which was around 80%. And these are the results that we have tried to consolidate here, that a basic random forest was able to perform well. So that I think this gives you a good understanding of how you shouldn't go after the most complex models, but actually we should be seeing which model will perform the best for our particular problem set. So for our particular problem set of binary classification, random forest worked pretty well for us, right? Why did one of the like the few reasonable conclusions that we have made is, one, it could be because overfitting. So your random forest is not going to overfit as much as your complex model like XGBoost. Second is the way you are tuning your hyperparameters, right? So the performance of complex models, they're highly dependent on the way on their hyperparameters, right? So if they're not tuned properly, then they can overfit. But as we had learned that random forests, they're quite robust to the choice of hyperparameters. Then it obviously depends on data characteristics. So random forests can perform very well on certain types of data. So for example, if they can handle categorical variables and interactions between features well, and hence they're not affected by scaling. So if your data has these characteristics, a random forest will outperform any complex models. Then noise in your data. If your data is noisy, then simpler models will perform better because they're much easier to generalize, because as a complex model, they'll try to fit the entire training data. So they are more likely to fit the noise as well. And then we have model complexity versus data complexity. So if the underlying data pattern is not very complex, then simpler models like random forest can capture the pattern well enough, and there might not be much benefit in using a complex model. Now, finally, how do we interpret the results? So this is where we'll consolidate everything that we have learned in all the previous sessions. So first of all, of course, we learned how to use some important libraries such as pandas, numpy, sklearn. Then we learned model selection. How we did the model selection was we trained and evaluated 4 different models, which is logistic regression, decision tree, random forest, and XGBoost. We learned how to scale our data. For that, we use standard scaler. And I think now you also know that there's another function called min-max scaler. And I think when you will be making your own project, you all will know in what circumstances you would prefer to use standard scaler or min-max scaler. We learned the different ways of splitting the data. So as we said that you could either split your data as a normal train test split, or you could split your data into test, train, and validation. And this is the code block wherein we have done that. And it's quite easy to use. Why we are using train test split twice? Because first we divided into 2 parts, and then the training data also we divided into to get the validation set out of it. So after you do all of these after you do train test split twice, you essentially get 3 subsets. So we learned what are the different ways of splitting our data, which is also an important thing to know. We compared our models using accuracy as our evaluation metric. We learned advanced model building using XGBoost. We did hyperparameter tuning on different models. So for XGBoost, we use grid search CV, random search CV. And to optimize our model, for example, we have optimized our XGBoost model by finding the best parameters. How we did that was using grid search CV and random search CV. We also, again, for the evaluation metric, for our particular problem set, we used accuracy as the evaluation metric. And finally, we have evaluated the performance of all of the models on one test set. And we saw that random forest with certain attributes or certain hyperparameters performed the best on our data set. So through this process, we have gained a much deeper understanding of how we can build, tune, and evaluate our machine learning models. And we have also seen how different models will perform on the same data set and how differently they learn to optimize their models. So I really hope that I understand that this session was really dense, but I really hope that there was something that you guys were able to take away from it. So I'm going to go back to my screen, to my slides, and I'll encourage you all to join our Slack channel, which is #BuildADataScience project, #BuildADS project. We encourage you all to put in your questions in that channel, because it would be easier for us to address all of your queries there. And finally, at the end of the, at the end, we will give you, our moderators will put in a feedback session. So we encourage you to fill that feedback session, because it helps us to improve our subsequent sessions. All right, before I give the session back to Mrudula, I'll just go through the chat and Q&A so that I haven't missed anything. Thank you, Louis. Thank you, Gagana. I really appreciate your text. Thank you, Jessica. I'll go through Q&A. Okay. Thank you so much for those lovely words. The regression explanation on the Jamboard and the links of the 3rd and 4th tab that were, yes, absolutely, I can do that. Yeah, so first of all, I can give you, I'm sending the link in the chat box. I am aware that sometimes the links don't work in the chat, so I hope,
you can actually answer the question on Q&A. If you type answer and you put the link in there, I think they're able to select it.
Perfect. That will be great. Okay, so I can just type in answer. These are essentially documentation that you can find on the easily on Google itself. Oops, when I said it, answered that as well. Okay. So you were asking about regression as well, right? Okay. So I think I'll go through the entire thing again, and I can just move on to a new page just so that it's easier for me to explain. All right. So logistic. Okay. I'm sorry, I'll just go through the question again, whether it was logistic or linear regression. Okay, regression. So I believe I'll just go through everything. Okay. So to understand logistic regression, it is important to know linear regression. Okay. So for linear regression, we say that let's take a different set. Okay. So let's say we are taking a data set again of Amazon order history, and we have only three features in our data set. We have one X feature, one Y feature, and then one target feature. So in the X feature, say that X feature could represent the price of your order, right? The Y feature could give maybe the category. I'm sorry because I'm actually trying to use my finger, so it might not be totally illegible, but I still hope you'll be able to understand something. And then we have the target variable, wherein we have the which is essentially the label of our data, right? That how are we classifying? So say the problem here is that we're trying to classify whether this particular item will be ordered by a particular user in the future or not. So 1 means that it will be ordered, 0 means that it will not be ordered. So what linear regression does is that linear regression is used for regression purposes, and by regression I mean that it will give us a continuous value. So for example, if the question was price prediction, that what will be the possible price using maybe the order history, then linear regression would work best. Why? Because linear regression will create a 3D space. Why? Because we have 3 variables here, right? So I'll say X, Y, and then we have target, which is nothing but your Z variable, right? And now here, essentially what we're doing is that target can be understood as a dependent variable, independent variable, and X and Y as your dependent variables. So what logistic regression does is that it will try to find this one line in this 3D space such that there will be different data points in your space, right? It's a little difficult to understand because it's 2D, but try to visualize that you have a 3D space, right? And within that 3D space, you're trying to make a line which goes through as many data points as possible, or as close to as many data points as possible, right? So what we're doing is that linear regression will try to minimize the distances between them, right? So these are our data points here, like these circles, and it will try to minimize the distance between these data points and the line. Therefore, we say that linear regression tries to find the best fit line. All right. I hope we are together till here. And once it finds the best fit line, what logistic regression does is that logistic regression converts this line into an S-line function. Why? Because see, we will not be able to do classification with linear regression. Why? I'll actually explain that as well. So let's say we have this 2D space wherein we have only one variable, that is we have one independent variable and one dependent variable, right? So what linear regression does is that we have these data points, right? And when we have many classifiers, right? So for a classification problem, right, we will have either 1 and 0. Say this is here. So in a classification data set, your data points will look something like this, right? Your 1 will be here, say your 0 will be here, right? So if you're using linear regression, most of the data points will actually work as outliers for you. And when they work as outliers for you, it means that it will be very difficult to make a best fit line because almost all of the data points will be outliers and it won't perform well. So that is why with linear regression, you cannot do classification. So to solve this problem, what logistic regression did was that this particular data point, which were like this, right? So if it's 1 here and 0 here, and if these are how the data points are, what it did was, see, a straight line won't work well, as we understood, but a S line would work perfectly, right? Because an S line would be able to identify all the zeros here and all the ones here, and similarly, right? And there would be only few, say, outliers here. So what logistic regression did was it converted that straight line into an S-line function. And we say that, say, 0.5 is the middle point here. And we say that whatever answer we get after applying sigmoid function, if that value lies above 0.5 or above midway of this S line, we will classify it as 1. Or if it is below, we'll classify it as 0. Therefore, logistic regression with this little tweak in linear regression can help us with classification. So I hope I was able to explain it a little better this time. And I hope that you guys understood. All right. I don't see any more questions here. So I'm going to give it back to Mrudula.
So thanks a lot, Siddhi, for such an informative session. And I'm sure that even all our attendees enjoyed it a lot. Another gentle reminder for everyone to join our Slack channel and our social media handles for any further assistance. And I think we'll wrap it up now. So thank you, everyone, all our moderators and Lindsay also. So thank you.